The biggest question I get on my videos is people asking where they can get their own robots for cheap. Today you're going to find out what I look for when buying used machines, how to get them running, and what can potentially go wrong. We're on our way to pick up more robots from a place in Ohio, about a 2-hour drive. They had an online auction a few weeks ago that I was able to win some robots from, a few more than I originally had planned on getting, so my friend is going to meet us up there with another trailer to help us haul them back. We were at 6-Axis Solutions, an industrial robotics integrator. They set up and repair robots for all sorts of companies. Any company can have an industrial auction that includes robots. For example, an automotive plant may clear out all of their old machinery when switching to make a newer vehicle. However, in this case, the company's entire thing is robots, so there was some pretty cool stuff here. Most of the items from the auction are already gone. This room is full of used robots that are still in good condition and will likely be put back into production. It's crazy how many there are all in one place and how clean they are. Most of the robots I see for cheap are completely coated in grease and dust. This is also my first time seeing the giant Fanuc M2000 robots, which absolutely tower over everything else. Some of them are big enough to mount one of these little R2000s on the end of it. I did find it kind of funny that the motors on them aren't much bigger than the motors on the R2000s. They just have 2 per joint instead of only 1, and 2 control cabinets to fit all of the servo drives. This place has a lobby that matches the robot theme. Lots of robots on display, along with one of the truest sayings I've ever read, and a flamethrower behind the desk. There's also an outdoor area full of older robots. This is the kind of condition I'm more familiar with. They're the ones you can often find for really cheap. If you're looking for a robot or need some integration work done, it might be worth reaching out to them. There's a link to their website in the description. Now the fun part begins. I need to get all the robots I won from the auction back home. My dad and I are in the truck with the bigger trailer taking the majority of the stuff. My friend has the rest in his car and U-Haul trailer, which is pretty hilarious. Running out of space was the only reason I ended up not getting even more. Most of the robots I got were sold as parts robots, so they're missing pieces and probably had something wrong with them to start with. That was the only way I was able to afford so many. Usually these small robots are very expensive since everyone wants them. They're the easiest to use and move. It's kind of ironic that the big robots weighing almost 3,000 pounds are almost always cheaper to get second-hand than the tabletop robots, even if they include controllers. No one wants to deal with moving the big robots around. As I take a look through these robots, I think now is a good time to talk about what I look for when buying used industrial items. I'm largely going to be talking about industrial robots, but most of the information and things to watch out for are the same for other industrial machines as well. Industrial auctions are a good way to get cheap machines, but aren't always super easy to deal with. They're normally run by an online auction house that you need to sign up and verify with before the auction starts. Then there's a couple days where you're allowed to look at the items in person to see their condition. Auctions charge a premium on top of the final item price, usually around 15 or 20%, and then an additional loading fee or even require you to pay a certified rigging company to come and load your items, which will almost certainly cost more than the robot if you're looking for a good deal. There are also industrial surplus stores that buy and resell industrial machinery, which are often easier to deal with than auctions. I've put links in the description to some of the places I've got machines from. If you get anything, be sure to tell them I sent you. It helps increase the chance of me being able to work with them in the future. Also, places like eBay or Facebook Marketplace will sometimes have good deals. However, by far the most powerful source of used industrial goodies is knowing someone who happens to be getting rid of stuff. More often than you'd think, robots get sent straight to the scrapyard. So asking around and knowing the right people can get you some robots for cheap or completely free if you're lucky. So how do you know what's a good deal? Well, a lot of it comes with experience. I'll put how much I spent on all the different robots and machines I've bought up on the screen to give you a better idea as they appear. First up is determining if it seems like it's in good enough condition or not, and includes all the required parts. For a fully operational robot, the biggest things are the robot itself, the controller, the teach pendant, and the cables to go between. If you only want the robot and plan on replacing the motors with your own, or using something like the open source robot controller I'm building, then you only need the robot and maybe cables if you can't find the mating connectors for sale somewhere. Robots without controllers will often be substantially cheaper than ones with, so they're what I usually get. Only one of the robots I got from the auction came with its original controller. Make sure everything looks intact. No missing motors, encoders, smashed connectors, or cut cables. I've seen a lot of damaged connectors from something bumping into the robot, or cut cables from people removing the robots from wherever they were installed. Apparently, the 5 seconds to unplug the cable is too long compared to the 3 seconds to cut it off. Tags or writing on the machine can be super useful. Many companies will tag faulty equipment and write the reason. Might be as simple as NFG, or maybe a bit more colorful and tell you what the actual issue is. Open or missing access covers are often not a good sign. Chances are someone was in there trying to fix a problem or steal a part to fix another machine. I always check extra close when I see something like that, and keep it in mind if I'm trying to troubleshoot an issue later on. If you're looking for a robot and controller pair, check that the numbers on the controller and robot match. Controllers are usually designed to run multiple robots using the same hardware with different software settings, but these settings aren't always easy to change or in the standard documentation. I didn't check the numbers matched on my FANUC R2000 I bought years ago and ended up getting a controller from a different model robot. I was unable to get it running with that controller, which was what started the whole open source robot controller project. Supposedly you can change settings deep in the controller to get it working, but I only had people tell me years after I had already sold the original controller and started making my own. I'm still making progress on the new version of my servo drives that are capable of running 3 motors from one board. Here the motors are running in open loop mode to test the drive itself and help me spot issues before ordering the next batch. Be sure to subscribe so you don't miss the full power testing. Thanks to PCBWay for helping sponsor these projects. They provide manufacturing and assembly services for custom PCBs, as well as custom laser cut and bent sheet metal, or CNC machined parts. They made all of the circuit boards and sheet metal enclosures for my robot controller parts, saving me a ton of time. The first 200 people who use the code PCBWay-Excessive Overkill 10 can get $10 off orders over $30. You can apply the code at checkout, or add it to your account to save for later. The discount code and link to sign up are in the description below. While testing my drives, I found I managed to flip some of the connections on all of the current sense amplifiers and had to do a lot of tedious bodges. I already have 4 more of these boards which are now non-functional in their current state, so they're going to be on my store as leftovers if anyone wants one. Not sure what you use them for, but they aren't doing me any good. My store is linked in the description if you'd like to check it out. The pre-order for the Development Edition light-up badges is also on there, and it's still open for another few days before I start manufacturing. If you want to get your hands on one, now's your chance. I'm only doing a limited run for this edition, so once they're gone, they're gone. Anyway, back to the video. Since my full controller isn't ready for sale yet, the best way to get a robot up and running is with its original controller. You should check inside of the controller to see if there are loose hanging connectors or empty slots, indicating a board might be missing. It's common for old equipment to have parts stolen to keep other machines up and running. Sometimes there are intentionally spare connectors or slots though, so it's really best to compare to the manual. The manual is probably the most important thing to find before you make a purchase. Maintenance manuals are incredibly valuable when it comes to getting old stuff like this up and running. Certain machines will have the manual or at least electrical schematics stored inside a control panel. Unfortunately, that's normally not the case with robots, and many brands like FANUC don't make manuals available to just anyone. You need to be a company with money to throw at them. So you might have to search online pretty hard to find any or rely on forums to read solutions to common problems. There are usually manuals for controller programming, controller maintenance, and robot maintenance. Finding all 3 is ideal, but the controller manuals can get you almost everything needed. I don't have the robot maintenance manuals for any of my robots. Now that you know what I watch out for, there's a couple things that aren't as big of an issue as you might think. such as if a robot is absolutely covered in grease and dirt. Sure, it might mean that the previous owner's maintenance program was a bit lacking, but there are some applications where robots will be absolutely covered in dirt after just one day, and they're built to handle it. Most robots are pretty well sealed up and will be perfectly fine with light water like from rain. Sitting outside for a while probably isn't going to hurt anything as long as all the parts are still attached and sealed up properly. If you see a machine that looks pretty bad, keep in mind other people are probably thinking the same, so it could be a good chance to get it for way cheaper than usual, if you are willing to maybe fix some problems or spend more time cleaning it up, that is. If the machine itself looks good, or good enough for the price, there are still a few other things to consider on your end. Industrial machines are big and heavy, so they aren't easy to move. However, I've yet to find anything that can't be moved with enough friends armed with crowbars and steel pins. Make sure you have a plan for how to safely get it where it needs to be. I highly recommend robots with bases already attached. They make it much more stable when sitting there and give you better mounting holes for bolting it down, which you definitely should do. Robots are very dynamic. The majority of the loads their mounting bolts need to handle are from the robot moving, not just the static load of it holding something still. Even if a robot seems stable when moving slowly, it may jump all over the place when running at full speed. You'll want to make it sturdier than you think and carefully test it up to full speed to see how it handles. You'll also need to figure out how to power the robot. Most industrial machines want 3-phase input power, which isn't commonly run to homes in the US. Some countries do have 3-phase, which is convenient, but you still might need a transformer to get the correct voltage. I live in the US and have standard 220 volts run to the house, so I built what is called a rotary phase converter. At its core, it's a normal 3-phase motor that is spun up and powered off of only single phase. Once it's running, it generates the remaining phases, although typically not super well, so some capacitors are often added to help balance out the voltages. These systems are common and pretty easy to build. You can get the parts for quite cheap if you're already looking at industrial surplus. However, that only gets me 3-phase at 220 volts. Some machines want 480 volts or even 560 volts. To get those voltages, I have a couple 3-phase step-up transformers, also bought as industrial surplus. The actual total power these robots need might be less than you expect. The supply requirements will usually be stamped on the controller or in the manual, but the average power is often significantly less. Robots are very peaky loads, so while moving slowly or stationary, they barely draw any power. But when doing fast moves, they can easily draw 10 or 20 times more for brief periods. My big robots are rated to only draw around 2.5 kilowatts on average. Smaller robots will use even less, as low as only a few hundred watts on average. You'll also need to plan out some safety setup. Unless you happen to find one of the fancy collaborative robots meant to work around people, any industrial robot you find will probably be capable of causing great injury to say the least. It might vary from breaking your hand to throwing you through a wall, but either way, you should stay out of reach and always be aware of what the robot is doing. Robots usually have teach pendants with special safety-rated switches you must hold down to enable motion. If you let go, the robot will stop immediately. They also have an e-stop button on the pendant and terminals in the controller for you to attach your own additional e-stop buttons, or safety sensors to tell the robot to stop if someone gets too close. Should you set up e-stop buttons and a whole safety enclosure around your robot? Yes. Do I? No, at least not usually. I almost exclusively run my robots in teach mode, which requires me to be holding the pendant for the robot to move. These robots can also run in full auto mode as well, which doesn't require you to hold the pendant. This is how robots run in production. Teach mode means I am at all times able to stop the robot in under a second by letting go of the safety switches or pressing the e-stop button, and I am paying attention since I know the robot is going to move. Then when I'm working around the robot and not holding the pendant, I have the e-stop button pressed or the entire robot switched off for extra insurance. If you choose to run in full auto to automate something, I highly recommend at the minimum painting the kill zone around the robot and setting up some barriers with e-stops around the room, especially if the area can be accessed by anyone who might not know the dangers of the robot. Ideally, the robot would be totally enclosed with safety scanners or light curtains to detect if someone was in the danger area, which would then prevent the robot from running. If you're going to buy e-stop buttons or safety devices, buy them from an actual automation supplier like Automation Direct. And not just any old button, get the ones meant to be e-stop buttons. And for sure not Amazon or AliExpress grade ones. I've seen way too many of those fail for me to bet my life on them. Once your safety setup is complete, test it thoroughly and test it regularly. Wires can get damaged or shorted together, so it's a good idea to make sure everything is still in working order periodically. With that out of the way, I'm going to try to get the one robot that came with a controller up and running. This next little portion is unscripted, so cut me some slack if I misspeak. First things first is getting this thing mounted, so if it moves, it's not going to fall off the table. Even though these are relatively small and relatively lightweight, I believe this weighs around 70 pounds, it is still well within its capability to break your finger or worse. I threw together this little wooden platform that I can just screw the robot base to and then bolt down to the metal table underneath, so nothing's going to slide around or move once this is running. Now, don't be deceived by the 220 volt sticker on the front. This is in fact a 3-phase controller, unfortunately. Our main 220 volt 3-phase comes into the top of this disconnect, which is accessible from the front of the controller, and basically turns on and off the main power to everything. After that, it runs down to this relay here, which is controlled by the e-stop board. This is the safety system for the entire controller and robot, which makes it so if you press the e-stop button on the front of the controller or on the teach pendant, it shuts down power to everything, so there's no chance of it continuing to run. It also has terminals that you can hook up to external e-stop buttons, such as whatever the robot ends up actually being built into. You'd typically want to have e-stops anywhere someone could potentially be within reach. It also has fence inputs, which are so there can be doors around the robot, and when those doors are open, they will break a contact and then trigger the robot to stop as well. Now, in our case, someone has already conveniently jumped over all of those safety inputs, so we should be good to go right from the start and not need to mess with any of that stuff. After this relay, the power goes into the bottom of this module on the left. This converts the 220 volts 3-phase into roughly 300 volts DC up at the top. After that, the DC power gets jumped to these two servo drives here, which are responsible for actually running the motors in the robot. The motors in there, I believe, are 200 watt servos, which are very small when it comes to industrial robots. This larger drive runs 3 servos, and this smaller drive handles the remaining 2. The module here is the main CPU, which actually handles all of the motion control, running the programs, connects up to the teach pendant. Basically, any of the actual processing happens on here. The servo drives themselves are extremely dumb. They don't do much of anything at all other than exactly what the CPU is telling the motors directly. The large connector here is the encoder feedback from the robot. Each of the encoders has, I believe, 2 twisted pairs that run back for data. One of them is the request signal sent from the controller to the encoder, and then the other pair is the data being sent back from the encoder to the controller. I believe this also connects to some of the additional kind of auxiliary controls on the robot, like the air solenoids built into it and the connector near the wrist on the end of the robot. This cable here is the teach pendant. This controller did not come with the teach pendant, unfortunately, but luckily this is an RJ2 controller, which is the same variant as the robot I have in the back there, so I can just take it from my other controller and bring it here to test with. The second cable that comes back from the robot is actually hidden underneath and runs to the bottom of these 2 servo drives, which is where all the motor connections actually go. So after having a good look over everything, I'm not seeing any loose connections or any of these modules that have gotten popped out of the rack they're supposed to be seated in. So I think we should be good to go. We can get power applied, get these cables hooked up to the robot, and see if this is going to move at all. The main reason I actually bought this robot was because I wanted these cables. I actually already have, I think, 3 other of this exact same robot model. One is actually attached to this sliding rail up here on this table. So I was never able to find the cables for these robots, but now I have them, which means I can figure out what the numbers are on them and get some more ordered, hopefully, if they are even still manufactured or there's new old stock of them somewhere. Very satisfying. I drilled holes in the corner of this piece of plywood, so I should be able to bolt this down to this actual table so the robot isn't going to slide all over the place if we are actually able to get it running at full speed. All right, nice and snug. Get the teach pendant, get 3-phase connected to that, and we should be good to try it out. Here's our teach pendant from my other controller. Hopefully there's nothing like horrifically wrong with this that ends up damaging this teach pendant, because I don't think I have any extras. All right, I guess nothing to it but to turn it on and hope for the best. All right, it's on. What do we got on the pendant? Diesel alarms, which means the encoder batteries in the robot itself are dead, which is not surprising at all. It's not really a major error. Pretty common on a robot once it sits for long enough. So the controller runs. So far everything seems like it's actually fully functional. The issue I'm having now is all these errors that are still set on the controller. The vast majority of them, or I believe actually all of them, are related to the batteries in the robot being dead. These robots actually have batteries inside of them that power the encoders on the back of all the motors. So whenever the controller is disconnected and normal power is removed from the robot, the encoders will actually stay powered and retain the position information to show the controller, whenever it's reconnected and powered back on, what position the arm is in. That way you don't need to recalibrate the whole robot every time you turn it on and off, which is super convenient. The downside is those batteries obviously do not last forever, and whenever they die, you get a whole bunch of errors and the controller basically refuses to do anything. There are switches on the back of the pendant that need to be held in for the robot to be able to move. You don't need to hold in both switches, but you need to hold in at least one. And it's meant so that you really need two hands to be holding this thing if you want to move the robot, because you need to hold in one of the switches on the back and press shift and press those jog buttons down there, which are now out of reach. So I might be able to do this with my other hand. Do some trickery here. I'm sure this is how they intended it to work. Anyway, you can see the error messages we get whenever I try to jog. Enable input is off. Now, I'm not sure where that enable input is. Okay, according to the internet, that MCTL-013, enable input is off, is related to some sort of software configuration in the controller itself. So I'm seeing a few different options here. One of them is this system variable. These buttons are not super functional. It's called OpWork, UOP disable. Pretty close. OpWork. UOP disable. 1. All right. We'll hit jog. Air status. Reset. Try again. No. Still won't work. I think we need to replace those encoder batteries. But at least we fixed the enable issue. That is progress. So I'm looking for the batteries here in the robot, and I kind of assumed they'd be there in the base since it's the easiest to get to, but they are in fact up here, conveniently covered by the top part of the arm. I have no idea how you're supposed to get at those if the arm happened to be in an even worse position where it was leaned back and there was almost no room above this cover. But there are 2 batteries in there They are these weird little industrial grade lithium cells or something. I'm definitely not going to have any of these laying around. So I guess I should probably get the correct replacements. But in the meantime, I think I'm going to find some other batteries I can plug in there and get this thing moving. Trying to test which of these pins are connected to see if these batteries are in series to get 6 volt or not. Yes, they are. Okay, that makes this easy. Then I can just put 6 volts and jump together these 2 inner terminals. Well, I guess they're already jumped together. I just need to put 6 volts on this pin to that pin. And since the connectors are polarized, I know which is positive and negative already. All right, we now have our replacement batteries. We need 4 of those since they're 1.5 volts each. These original ones were 3 volts. They're just wired in series in the robot. And to hold them, I unfortunately did not have a single 4-cell battery holder. So I have a 3-cell and a 1-cell soldered together with the connectors I cut off these old batteries where they should be. So we should be able to plug all this in and get it to fit. And then this one goes here, this one goes here. Leave that cover open for now. Whoops. Well, in my haste to plug everything in and try this out, I accidentally swapped the connectors whenever I plugged them in, which instead of the 6 volts being on the outer pins going to the encoders, the 6 volts was on the inner pins, which that little circuit board shorts together. So these batteries were just a dead short, and it actually ended up getting hot enough that it melted one of the contacts out of this little battery holder. I could smell it and immediately knew I messed up. So I unplugged it right away, but that battery holder is already toast. All right, so after that, I went for the much simpler and bit more reliable solution. You just have a power supply hooked up there now. Now, if I shut that off, the robot's going to forget where it is and lose all the encoder position information. But just for testing, that is perfectly adequate for now. Yep, we only have the pulse not established errors, which are in our case acceptable because I haven't moved it yet. Now comes the moment where I can try moving this thing. It is not calibrated yet, so none of the soft limits are going to work. We're going to need to be careful. Oh, it's on. I hear the servo drives whistling away. Now I can try to move each joint very slowly. All right. Oh, would you look at that? They all move. Disturbance excess. That's not a good sign. Which joint is that? 5? Does it come back? Could have been if it just sat for quite a long time. It was a bit stiff to start. But it very well could be that one or more of the harmonic drives that run each joint could be in not super great condition. All right, next up is going to be getting all the joints recalibrated so it is mastered, as Fanuc calls it. And to do that, all we need to do is line up all these little witness marks. There's one on each joint. They all need lined up to the 0 position, and then we can calibrate it in the teach pendant, and we should be able to get into actually running programs at full speed and also doing XYZ jogging. All right, so I just finished mastering all the joints and everything is saved and updated. Should be good to go. So previously we could only jog in joint mode, which is where we were controlling each joint individually. What it being all calibrated now will let us do is jog in XYZ mode. There's actually several different modes, but they all follow the same sort of general idea where we're controlling the actual end point of the wrist instead of individual joints. So we'll be able to jog the end point of the wrist in straight lines relative to the overall world rather than just the joints on the robot. Basically, all of the joints are going to move together to maintain a straight path for the end point of the wrist to move in. Now, we're going to start this off nice and easy at 10% jog speed. And we're going to try moving in Z first. Yeah. Z down. Seems right. Yeah. It looks straight to me. All right, then we have X, which is forward and backward. And then Y, which is side to side. And then we can try going a bit quicker. We'll go up to 50%. It's actually pretty quick. Now, this speed is of course nowhere near the actual max speed of the robot or the joints. In any jog mode you're in, the joint speed, or at least the linear move speed, is typically limited quite a bit below the actual maximum speed of the joint and the robot. That way, whenever you're jogging around, you kind of need it to be slower to have the proper control. Once a program is written and the points are all predefined, you can crank up the speed to the maximum and we'll be able to see how quick the robot can actually move then. All right, now that the robot is basically completely up and running, we have it calibrated, moving in XYZ position as well as joint positions. We should be ready to finally write some programs and then see this thing run at full speed. Programming these robots is incredibly simple. The main way is by jogging the robot to whatever positions you want it to be in, and then it'll basically play them back in whatever order you specify in the teach pendant. And that'll let us run it at full speed compared to the limited speed we have now when we're just jogging. So I'm just going to write a simple test program, exercise the joints a little bit, move around, basically not do anything, but just see how fast this thing can actually go. So I wrote a quick little test program. It should basically just exercise each joint and then do a couple linear moves. We are going to start it at 25%, which I think is pretty reasonable. The joint moves are all set to 100% speed and the linear moves are set to 500 millimeters per second, which I think isn't quite full speed for this robot. I think full speed might be like a meter a second. But the joints are going to move full speed regardless for the normal joint moves. So we can try this out and see how fast it can go. Alright, well that all seems good. Should we do 50? Nah, we'll just go right to 100. Hopefully nothing has any problems. Maximum speed. Pretty quick. Pretty quick. I'm excited to see how quick the newer versions of this one will be able to go. I assume they're quicker than this. This is one of FedEx's very first LR mates, I believe. From... what year is this? Oh wow, this is actually a pretty modern one. This is from the year 2000. I think I have some that are from like 1997. This one up here is 1998, so pretty old. The newer ones down there, and they have some really new ones that are still current. They'll be 6-axis and everything, so very excited to try to get those working eventually. I need the open source robot controller for them though. They did not come with any of their own original controllers. So that'll be a project for another day, but eventually I'll get some of those running up at full speed, just like this one is. The dead batteries are basically the standard issue with FedEx robots after they sit for a while. Not at all a big issue to fix. There are a few other issues that are also usually easy fixes, but some can be huge problems. If you have issues with the controller, the first thing is to check what the errors mean in the controller manual. It usually has great instructions for how to go through and fix the issue. Often there might be fuses blown due to improper or damaged wiring. Most controllers have a fuse scattered about for control power and logic. That's one of the first places to look if you are getting really bad sounding errors or it won't power on at all. Of course, you should have a look to see why the fuse blew in the first place. Could be bad wiring, could be a bad part, could be something that used to be connected had failed and is now gone, but the fuse was never replaced. Just make sure you aren't blindly replacing fuses without knowing the original issue. You could potentially cause even more damage. There's also the signature culprit in all electrical systems: bad connections. Always check connections first if there's an issue. The contacts themselves could be dirty, the connector might not be fully seated, maybe a solder joint has cracked. I've seen cables and air lines in robots completely worn through after thousands of movement cycles, or small nicks in cables that cause intermittent connections or shorts. The list is endless. What I'm getting at is, verify your connections first before you start tearing everything apart. The other common issues I've seen that are less easy to fix are the mechanics of the arm itself. Chances are any arm you find will have AC servo motors in it, unless it's very old, in which case it may have DC brushed servo motors. Basic stepper motors are uncommon in industrial grade machines since they have much lower power density than those other motors. AC servos are typically reliable, but can still fail as you'll see in a moment. DC brush servos are much more likely to be worn out and need to be cleaned and have new brushes installed. I have also seen the brakes attached to the motors fail. Most robot servos have spring-loaded brakes attached to their motors that require power to unlock. Robot joints are usually back drivable, so if the motor isn't being powered to hold its position, the arm would flop down. The brakes hold the motor in place by default with no power, so the arm doesn't fall. The brakes are sized to provide a bit above the continuous torque output of the motor, so if the robot loses power while moving and the brakes slam on, the stopping torque is still within the acceptable range. The brakes shouldn't damage anything if they're needed to stop the robot from full speed. However, during normal use, they only ever hold the motor stationary and aren't actually handling slowing down the motor. The normally locked brakes introduce a couple important considerations. If you manually send power to the brakes to release them, or remove a motor to work on it, the arm may fall. Or in some cases, if the arm has a counterweight or big counterbalance spring, it might instead rise. I've heard stories about people removing a motor on one of these big robots and sending the end up into the ceiling from the counterweight falling. I generally short the motor phases together if I want to release the brake on a joint. It makes the motor stiff to turn, which prevents the joint from moving fast, and keeps everything nice and slow. I got a box of assorted robot parts from the auction, including a couple motors that say they have bad brakes. On a good motor and brake, the shaft will normally be locked in place. A small amount of backlash is fine. Then when power is applied to the brake, it'll be free to rotate. On the bad motor, the brake still draws power and even makes the click sound like it's releasing, but the shaft stays locked in place. There is also no backlash at all, unlike the good motor. I decided to take the motor apart to try to find what the actual failure reason was. It turns out the brake itself is fine. It releases and moves freely like it should. The real issue is the rotor itself has come apart. The magnetic dust covering it caused it to jam up against the inside of the stator and prevent it from turning. This is unfortunately unrepairable. Even if I cleaned off all the dust and reassembled the motor, the magnetic properties of the rotor have changed and the motor won't perform as well as it should. Not to mention, I also managed to scratch the encoder code wheel while I was trying to get it off the shaft it was glued to. These small motors are not at all easily serviceable. If only the brake failed, it could possibly be fixed, or just totally removed. Then the motor could still be used for something else, as long as it being allowed to rotate when powered off is okay. One of the worst problems to have with these robots is the gear reducers themselves failing. They are what connect each joint to the next. They contain a set of bearings keeping the joints together, and also some sort of gear reduction that lets the relatively fast servo motors drive the relatively slow joint with very high precision. Although as you've seen, relatively slow can still be pretty fast. After years of use, they can end up getting sort of crunchy and stiff to turn, or start to have more backlash than is acceptable. Not only are the replacements expensive and hard to find, they're a huge mess to replace since they're full of grease. Even the grease is super expensive and specialized for each robot and reducer type. On the robot I just got running, you may have noticed how loud and squeaky the joints sounded when they moved at full speed. You might think the gear reducers or motors are shot, but that high-pitched sound is mainly from the servo drives running the motors. Older robots typically have servo drives with a lower switching frequency, which makes them sound louder. So don't be immediately alarmed by the high-pitched squeal the joints make when moving. There are two common types of gear reducers used in industrial robots. Small robots use harmonic drives, also called strain wave gear reducers. The one I have here is a brand new frameless harmonic drive. The ones in robots are usually a bigger integrated unit including bearings and seals to keep the grease in. This one is only the actual reducer. It's meant to be put in a machined housing with bearings and seals added separately. They have a thin flexible inner spline and rigid outer spline that has two more teeth than the inner one. Then a bearing fits snugly inside the flexible spline. Crucially, this bearing isn't a perfect circle, it's actually a slight ellipse, bending the flex spline so it meshes with the external spline at two sides. The input to the reducer is the center of that bearing. When it rotates, it moves where the splines are meshed together. The output is between the inner and outer splines, which would be connected to each side of the robot joint in this case. Since the outer spline has two more teeth than the inner spline, each time the input rotates one full rotation, the inner and outer spline move by two teeth as well, resulting in a total reduction between 50 to 200 to 1 typically. These reducers don't always have a graceful failure where they slowly wear out, however. This robot has been through some sort of substantial crash. The J2 reducer is completely destroyed and the joint is free to move. The J3 reducer is still at least partially intact, but it's stiff to move and not at all smooth like it should be. After pulling it apart, it's clear this joint has also suffered a crash. The flex spline has started to twist and buckle in on itself. Those bumps in the flex spline aren't supposed to be there. It should be perfectly round like the new one. This kind of failure requires the reducer to be replaced. There's no repairing the flex spline. These were listed as parts robots like I mentioned before, so I will eventually tear apart all of them and see what parts are good and what needs to be replaced, then build as many complete robots from the good parts as I can. The remaining good parts will either be used for other projects, kept as spares, or put on eBay to help fund future projects. The bigger robots don't just use giant harmonic drives. Instead, they use something called radial vector reducers, or RV reducers for short. I'm not going to take apart one of my big robots to show you a reducer, but luckily I got some brand new RV reducers as industrial surplus years ago and haven't used them for anything yet. This is a relatively big one. All of the joints on robots this size typically use RV reducers. My UP6 has small RV reducers on joints 1, 2, and 3, with the rest being small harmonic drives. I think harmonic drives are easier to manufacture once the joints need to be so small. I even have some insanely small ones about the size of a quarter. RV reducers have cycloidal discs surrounded by pins they mesh into, with the count being off by 1 between them. Since the lobes are so much bigger than the teeth on the splines and harmonic drives, there aren't as many and the reduction ratio is lower. To help with this, there's an additional reduction between the motor and the cycloidal disc through standard spur gears that brings the reduction back to a similar range as harmonic drives. Now don't be fooled into thinking this is a planetary gear reduction. There is no outer ring gear that the larger spur gears are running against. Instead, they're attached to offset crankshafts that drive the cycloidal discs. This method of driving the discs from multiple points with much larger bearings is what separates RV reducers from plain cycloidal reducers, which are usually only driven from a single offset crank in the center. The pins on the outside are also able to rotate, which changes the bearing or wear surface from the small point where the cycloidal disc contacts the pin to the large cylindrical surface the pin is seated against, reducing friction and greatly improving the life of the reducer. The bearings supporting those crankshafts might seem oversized for handling the loads from those relatively small input gears, and that's because they are. Those crankshafts and bearings are what carry the full output torque from the cycloidal discs to the joint the reducer is driving. There are 2 cycloidal discs in this reducer. If you look past the top disc, you can see a second disc moving around underneath. Technically, only one disc would still work. The reason there are 2 discs is for balance and additional rigidity. A single disc would create quite a bit of vibration as it oscillates since it's off-center. The second disc is designed to move in the opposite direction as the first, so the vibrations cancel out. This also means the loads on the crankshafts from the cycloidal discs are balanced. Each shaft is pushing the discs in opposite directions, and the discs mesh on opposite sides of the outer housing. That way, the oscillating load from the discs mostly stays contained to the crankshaft's discs and housing, rather than needing to go through all of the other bearings to keep the discs meshed with the outer pins. I'll eventually work on getting some of these other small robots up and running, maybe make another video out of it. But first, I need to clear out space in the garage to work on the mobile robot arm, so into storage they go. If you found this information helpful or want to keep up with my projects, be sure to like and subscribe. Thanks for watching.